Hello class! Today, here in Advanced Engineering Mathematics for Civil Engineers, we are now going to discuss our second lesson, which is about matrix. Okay, so for this topic, we will have the following intended learning outcome. So students must be able to discuss the different types of matrices and perform various operations. Let us first define what is matrix. So, matrix, it is an ordered rectangular array or arrangement consisting of elements written in rows and columns. So, this is invented by Arthur Cayley. So, there are actually a lot of applications of matrices in engineering, like solving a large system of equations. So, we can use matrix in solving those. No? So, let's proceed. Okay, so this is the general representation of matrix. It is denoted by a capital letter. So this matrix, okay, so this is actually denoted by capital letter A. So it is also enclosed by a bracket or parenthesis. So this matrix, it is enclosed by a bracket. Okay, so A sub 1, 1 up to A sub Mn are called elements or entities of matrix A. So this A sub 1, 1, this A sub 1, 2, this A sub 1, 3, up to A sub Mn, these are called elements. So this is element A1, 1, this is element A1, 2, or A sub 1, 2. No, so these are called elements, okay, or entities. So the subscript of the element determines its row and column position. So the row is the horizontal arrangement, okay, of the element. So these are the row, okay. So these are the row, okay, and your column will be the vertical arrangement, okay. So this will be the column. Okay, so the subscript in our elements here, it indicates, okay, the row and column where that element is located. So, for example, for A11, no? So, A sub 11. So, its subscript, the first subscript, which is 1, meaning to say it is located in the first row. Okay, and this second subscript, meaning to say it is located in the first column. So, this element is in the first row and first column. Now, let's say for A sub 2, 3, okay, so the first okay, subscript, it will be for the row. So it will be, it is located in second row, and this second subscript, this is 3, so this is located in the third column. Okay, so that's how you put the subscript, no? So it determines the rows and the column position of the element. So also, we are calling this matrix as M by N matrix A. So M by N is actually the size of this matrix. So we name the size of this matrix by M. So yung M dito, this M is actually the row, and this N is actually the column. So we name it your matrix this way, M by N matrix A. Okay. Okay, so let's talk about the size and order of matrices. So the size of a matrix is described by specifying the number of rows or the horizontal lines or arrangement and columns or vertical lines or arrangement that occur in the matrix. So I've mentioned this already that when you name the size of a matrix, okay, you have to specify first the row. Okay, and after that is the column. So the size of a matrix is row by column. Okay, so let's say you have 5 rows. Your matrix has 5 rows and have 3 columns. Okay, so that matrix is actually 5 by 3. The size of that matrix is 5 by 3. So it should be row first, okay, row by column. Okay, and also for the order, so the order of a square matrix depends on the number of rows. So only matrices that are square, okay, have order. Okay, so square matrices are matrices that have equal number of rows and columns. Okay, so those are the square matrices, no? They have equal number of row and columns. No, so only square matrices has order. So the order for square matrix, it depends on the number of rows, which is also equal to the number of column, right? Since it is a square matrix. So other matrices that are not square has actually no order. Okay. Now, let us classify the following matrices according to size and order. So, for number 1, this matrix A, okay, so we will determine its size. So its size again is row by column. So let's count the number of rows. Again, the rows are the horizontal arrangement of your elements. So this will be 1, 2, 3. So there are 3 rows, and for your column, that is the vertical arrangement. So the number of columns are 1, 2. Okay, so that will be the size row by column. So that will be 3 by 2. So that will be the size of matrix A. Now, for its order, again, only square matrices, okay, have order. So meaning to say, this matrix A is not a square matrix since the number of rows is not equal to the number of column. Therefore, this matrix A have no order. Okay, and for number 2, this is matrix B. So again, we will determine its size. So its size will be row by column. So the number of its row is actually 1. Okay, so 1. And its column will be 1, 2, 3, 4, 5. So this matrix, its size is 1 by 5. Okay, so also for matrix B, this matrix have no order, right? Since this is not a square matrix. Now, for number 3, so its size will be, again, row by column. So that will be 1, 2, 3, and its column will be 1, 2, 3. So this is a 3 by 3 matrix. Now, since this is a square matrix, its order will be its number of row. Okay, so the order for number 3 or for matrix C is 3. Okay. Now, for number 4, okay, its size, again, is row by column. So, the number of row will be 1, 2, and the number of column will be 1. Okay, so this will be 2 by 1. Its order will be no order since this is not a square matrix. Now, for matrix E, okay, so its size is 1 row and 1 column. So, this is 1 by 1. And its order will be the number of its row, which is 1. So, the order is 1. Now, for number 6, this is matrix F. So, the size will be row by column. So, its row is 1 and its column is 1, 2. So, this will be 1 by 2. And its order will be no order since this is not a square matrix. Now, for matrix G, so its size will be 1, 2 by 1, 2. So, this will be 2 by 2. And its order will be the number of row, which is 2. So this will be the size and order of these matrices. So let's proceed now to types of matrices. So the first one is square matrix. So for square matrices, the number of rows is equal to the number of columns. Okay, so here, this matrix A actually has 3 rows and 3 columns. So the number of its rows and the number of its column is equal, right? So therefore, this matrix A is a square matrix. Now, the second one is the rectangular matrix. So, in rectangular matrix, the number of rows is not equal to the number of columns. So, this matrix B, this is a rectangular matrix since the number of rows is not equal to the number of columns. No, so this matrix B is a rectangular matrix. So the third type of matrix is called row matrix or vector row. So it is a matrix that has only one row. So here, this matrix C, it only has one row. So this is a row matrix. Now for the fourth type, this is called column matrix or column vector. So it is a matrix that has only one column. So this matrix D only has one column. So this is a column matrix. The fifth type of matrix is called diagonal matrix. So in diagonal matrix, at least one element of principal diagonal is non-zero and all the other elements are zero. So the principal diagonal that we are referring here is this diagonal. Okay, so this is the principal diagonal of a matrix. So your principal diagonal is not here. It cannot be this. Okay, so the principal diagonal again is this. No, so you can say that this is a diagonal matrix if at least one element, okay, from this principal diagonal is non-zero. Okay, and also class, only square matrices has principal diagonal. So rectangular matrices have no principal diagonal. Okay, so again, this is the principal diagonal, and for diagonal matrix, okay, at least one of the elements of this principal diagonal should be non-zero. Okay? And all the other elements should be zero. These other elements, okay, it should be zero for you to say that this is a diagonal matrix. Now, for number 6, this is called scalar matrix. So, for scalar matrix, all the diagonal elements are the same. So, the principal diagonal, okay, you can say that this is a scalar matrix if all the elements here in the principal diagonals are the same. Okay, so they are called scalar matrix. Now, for the seventh classification or type, so this is called identity or unit matrix. So, if all diagonal elements are equal to 1, no, so they are called identity matrix. Again, if all the diagonal or principal diagonal elements are 1, okay, so they are called identity or unit matrix. So, this is denoted by capital letter I. So, as you can notice here, that there are matrices that has two or more classification, okay, or type, okay, that they belong. Okay, so let's say for this identity matrix, so this can actually be a scalar matrix also, right? Since all the diagonals are the same. And also this can be a diagonal matrix also. So this can also be a square matrix, right? So a matrix can have two or more types of matrices, no? So that can happen. The eighth type of matrix is called triangular matrix. If all the elements above the principal diagonal are zero, so that is called lower triangular matrix. Or all of its elements below the principal diagonal are zero, that is called upper triangular matrix. So they are called triangular matrix, no? So these are examples of triangular matrix. So this matrix G, so since the elements above the principal diagonals are all zero. Okay, so this is called lower triangular matrix. So the triangle form here is this triangle. Okay, that's why it's called lower triangular matrix, no? Now for matrix H, no? So since the elements here below the principal diagonal are all zero, okay? So this is called upper triangular matrix. So the triangle form here is this triangle. So this is upper, no? This is in the upper part of the matrix. So that's why it's called upper triangular matrix. Okay, so these are triangular matrices. Now, for the ninth type of matrix, this is zero matrix. So, for zero matrix, all the elements are equal to zero. Okay, so zero matrices are denoted by capital letter O. Okay, so regardless of the the size of the matrix, okay, so as long as all the elements are zero, they are called zero matrix. Okay. Now, let's proceed to the operations on matrices. So, the first operation is addition or subtraction. So, our rule for addition and subtraction of matrices is this. So, if A and B are any two matrices of the same size, they should be the same size. The matrices that you are adding, okay, they should be same size, okay, so that you can add them. Then the sum A and B is the matrix obtained by adding together the corresponding elements in the two rows. Okay, so that's how we add matrices, no, of the same size. We just add the corresponding elements. So let's say for element in the first row, first column of the first matrix, it will just be added to the same element of the same position, okay, of the second matrix. Okay, so that's just how you add, no, matrices. So again, matrices of different sizes cannot be added. Okay, so if your matrix A and matrix B don't have the same size, okay, they cannot be added. Okay. So let us consider the matrices here. We have here matrix A, matrix B, matrix C, and matrix D. And we are asked here to solve for A plus B, or the sum of matrix A and matrix B. For the second one, it will be A plus C, then C plus D, A minus B, then D minus C. So we are going to solve this. For letter A, this will be the solution. Okay, so for letter A, that is A plus B. So this will be the matrix A and this will be the matrix B. Okay, so the first thing that you have to do before starting to add these matrices is to check first the number of, or the size rather, the size of these two matrices. So they should have the same size. So for matrix A, its size is 1, 2, 3, 3 by 1, 2, 3, 4. So this is 3 by 4. So for the second matrix, which is B, so its size is also 1, 2, 3, 1, 2, 3, 4. So this is also 3 by 4. So meaning to say we can add these two matrices. So our rule again for adding two matrices, we just add the element to its corresponding element. Okay, so let's say this element, which is 2, so its corresponding element in the matrix B is this element. So this will just be 2 plus 1. Okay, so that will be 3. Now for the next element, that will be 1 plus negative 6. So that will be negative 5. And then 0 plus 3. So that will be 3. And then we have here 3 plus 3. That will be 6. Now for this element, this will be negative 1 plus 4. So that will be 3. And we have here 0 plus 1 fourth. That will be 1 fourth. Now, for 2 plus 0, that will be 2. Then 4 plus 4 fifth, that will just be 24 over 5. And then we have here 4 plus 4, that will be 8. And then we have here 4 plus, negative 2 rather, negative 2 plus 3, that will be 1. And then we have here 7 plus 0, that will be 7. And then we have here 0 plus 0, that will be 0. So this will be the sum, okay, or the addition of these two matrices. So this will be the answer for this. Now, for letter B, this is A plus C. So this is the matrix A and this is matrix C. So again, before we add this, okay, we have to determine first if they have the same size. So the size of matrix A is 3 by 4 and the size of matrix C is 2 by 2. So meaning to say, since they have different sizes, okay, so these matrices cannot be added. Okay, so this will be the answer for this. It cannot be added. Now, for letter C, this is C plus D. So, this is matrix C and this is matrix D. So, since these two matrices have the same size, so they are both 2 by 2 matrices, right? So, we can add these two matrices. So, this is how we add these two matrices, no? So, this will be cosine squared t plus sine squared t. So, cosine squared t plus sine squared t is actually Pythagorean identity, right? And that you know that that is equal to 1. Okay, so cosine squared t plus sine squared t will be 1. And then we have here t plus 2t, that will be 3t. And then we have here e raised to t plus 3, that will be e raised to t plus 3. Okay, we cannot simplify that further, no? And then we have here 5 plus negative t squared. So that will be 5 minus t squared. So this will be the addition or sum of these two matrices C plus D. This will be the answer. So let's proceed now to letter E. So we will skip letter D, okay? So I will leave that problem to you, okay, for you to answer. Okay, so we will now proceed to letter E. So this is D minus C. So for D minus C, okay, so this is matrix D and this is matrix C. So again, they have the same size, so we can subtract them, no? So to subtract this, this will just be sine squared T minus cosine squared T. Okay, and we have here 2t minus t. Okay, and then we have here 3 minus e raised to t. And then we have here negative t squared minus 5. So this will be the difference, no? So this will be the difference of D and C. Okay, so from here, we can actually simplify this further. So sine squared t minus cosine squared t, don't get confused. This is not equal to 1. Okay, what's equal to 1 is sine squared t plus cosine squared t. So this is sine squared t minus cosine squared t. But if you are going to recall from your trigonometric identities, okay, so as you can see here, this can be this, right? Cosine squared u minus sine squared u. The problem here is that they have the opposite sign, no? So it should be negative and this should be positive, no? But we can actually factor out negative here so that we can transform this sine squared t minus cosine squared t into cosine squared t minus sine squared t. So we can factor out the negative sign. No, so after factoring out the negative sign, okay, that will now be equal to negative cosine 2t. Okay, so this sine squared t minus cosine squared t, this is also equivalent to negative cosine 2t from this identity, no, in your trigonometric identities. Now for 2t minus t, that will be t, and then 3 minus e raised to t, we cannot simplify that further, and then we have here negative t squared minus 5. So also we cannot simplify that further. No, so this will now be the answer for letter E. So let's proceed now to the second operations on matrices, which is called the scalar multiplication or scalar division. Okay, so let K be a scalar quantity. So scalar quantity meaning to say they are constants. Okay, so let's say we have here matrix A. Okay, so let's say we have here K times A. Okay, so this K is a scalar quantity or a constant. No, so if this is matrix A, okay, if we are going to perform this operation, this will just be K times this matrix, okay, and what you're going to do here is just multiply that K to each element. So this will just be K times A, this will just be K times B, K times C, K times D. Okay, so this is a scalar multiplication, no, that this operation, no, and also there's also a scalar division, okay, where we can divide our matrix by scalar quantity K. Okay, so again, K is a constant, no? So let's say this is matrix A, no? So divided by the scalar quantity K. So what we're going to do here is just every element here will just be divided by K. So this will be A divided by K, that will be A over K, then B over K, then C over K, then D over K. So this will be the answer for this operation, no? Okay. So let's start solving problems about scalar multiplication and scalar division. So let's consider the matrix A here. So these are the elements of matrix A. So if K is equal to 3, find AKA and letter B A over K. So we will apply a scalar multiplication and scalar division here. So for our solution, so again, we are asked here to solve for KA, wherein K, okay, is equal to 3. Okay, so your K is equal to 3 and your matrix A is this matrix. So what we're going to do here is just multiply this scalar quantity 3, no, to every element, okay, in this matrix. So this will just be 3 times 2, 3 times 1, 3 times 0, 3 times 3, and so on, no? So this will just be 6, 3, 0, 9, negative 3, 0, 6, 12, 12, negative 6, 21, 0. So this will now be the answer for this operation KA. Now, for letter B, this is A over K. So we will divide our matrix A by scalar quantity 3. No? So what we're going to do here is just divide every element of our matrix A by 3. So this will just be 2 over 3, 1 over 3, 0 over 3, 3 over 3, negative 1 over 3, and so on. No? So dividing this, no? So this will just be 2 over 3, 1/3, 0 over 3, and then that will be 0. 3 divided by 3, that will be 1. Negative 1 over 3, that will be negative 1/3. 0 over 3, that will be 0. 2 over 3, that will be 2/3. 0 over, or 4 over 3, that will be 4/3. 4 divided by 3, that will be 4/3. Negative 2 over 3, that will be negative 2/3. 7 over 3, and then 0 over 3, that will be 0. So this will be the answer for this item, no? A over K. So this is the answer. So let's proceed now to the third operations on matrices, which is multiplication. So this is multiplication of matrices. So our rule here, if A or matrix A is an M by R matrix and matrix B is an R by N matrix, then the product AB is M by N matrix. So the rule here to multiply two matrices, okay, let's say we have here M by R matrix and we have here R by N matrix. So our rule here, no, so the column, okay, of your first matrix or the number of column of your first matrix, okay, it should be equal to the number of row of your second matrix. Okay, so they should be equal, okay, for us to be able to multiply them. If they are not equal, then they cannot be multiplied. Okay, so meaning to say, the arrangement, okay, the arrangement of how you multiply matrices, okay, is also important because if R by N, okay, will be put in the first position and then M by R in the second position, they will not have the column of that first matrix, which is N. It will not be equal anymore to the row of the second matrix, which is M by R. No, so it is important, the arrangement is important, no, for multiplying matrices. And the product of these two matrices, okay, it will be determined, okay, from the size of the row of the first matrix and the column of the second matrix. So this will indicate, okay, the size of your product AB. Okay, so the size of the product AB will be M by N. Okay, so that's how you multiply matrices. So now let's consider matrices A and B. So this is matrix A and this is matrix B. So we are asked here to find for AB and then BA. No? So let's start solving this. So let's solve letter A. No, so our letter A is a product of A and B. So this is AB. So this is matrix A and this is matrix B. Again, before we multiply these two matrices, we have to check first if they can be multiplied. Okay, so the size of matrix A, this is 2 by 3, right? 2 rows and then 3 columns. Okay, and the size of the second matrix is 3 rows and 4 columns, so that will be 3 by 4. So our rule here, for this matrices to be multiplied, okay, the column, okay, or the size of the column of the first matrix, okay, it should be equal to the size of the row, okay, of the second matrix. So since they are equal, they are both 3, no? So these matrices therefore can be multiplied, no? So after that, we can determine the size of the product of these two matrices, okay, by the row, okay, of the first matrix and the column of the second matrix. So the resulting size, okay, of the product of A and B will be 2 by 4. Okay, so let's start multiplying this. So this is the rule for multiplication also for matrices. You have to multiply, okay, the first row to the first column of the second matrix. Okay, so you have to multiply this first row of the first column, rather first matrix rather, no, to the first column of the second matrix. So that will be your first element located in the first row and first column. Okay, so this will just be 1 times 2 and then 2 times negative 1 and then 4 times 4. Okay, so you will multiply them that way. Again, that will be 1 times 2, and then 2 times negative 1, and then 4 times 4. So those product, you will add them. Okay, so this will be the sum of those products. No, again, that will be 1 times 2. That's why it will be 1 times 2 plus 2 times negative 1 and then 4 times 4. So the answer for this, no, for this will be the element, okay, of your product located in the first row and first column. Okay, since the rows and columns that we have multiplied here are in the first row and in the first column. Therefore, this element will be located in the first row and first column. Now for this element, okay, we just have to multiply since this element is located in the first row and second column. We are just going to multiply the first row here in the first matrix to the second column, okay, of your second matrix. So that will be this row and this column. So we are going to multiply that. That will be 1 times 1, okay, plus 2 times 0 plus 4 times negative 2. So that will be 4 times negative 2. Now for this element, okay, so this will be the product of this row and this column. Okay, again, this row, okay, and this column, since this is located in the first row and third column. So this will be 1 times 0, okay, plus 2 times 2, okay, plus 4 times 7. Okay, so this will be that. Okay, now for this element, this will just be the product of this row and this column. So this will be 1 times 3 plus 2 times 4 plus 4 times 0. Okay. Now, proceeding to the next row. So, what we're going to multiply here for this element will be the second row of the first column or first matrix rather. Again, second row of the first matrix, you multiply that to the first column of the second matrix. Okay, for this element located in the second row and first column. No, so this will be 2 times 2 plus 6 times negative 1 plus 0 times 4. Okay, now proceeding to the next element. Okay, so this will be this row multiplied by this column. So this will be 2 times 1, okay, plus 6 times 0, okay, plus 0 times negative 2. Okay, now for the next element, it will just be the second row here and the third column here. That will be 2 times 0 plus 6 times 2 plus 0 times 7. Okay, so for the last element here, so this will be 2 times 3 plus 6 times 4 plus 0 times 0. Okay, so solving for the values of this, so this will be the elements now of the product of A and B. So 1 times 2 plus 2 times negative 1 plus 4 times 4, that will be 16, right? And then we have here 1 times 1 plus 2 times 0 plus 4 times negative 2, that will be negative 7. And we have here 1 times 0 plus 2 times 2 plus 4 times 7, that will be 32. And we have here 1 times 3 plus 2 times 4 plus 4 times 0, that will be 11. Okay, and we have here 2 times 2 plus 6 times negative 1 plus 0 times 4, that will be negative 2. And we have here 2 plus 6 times 0 plus 0 times negative 2, so this will be 2. And we have here 2 times 0 plus 6 times 2 plus 0 times 7, so that will be 12, right? So for this, so this is um so this is 2 times 3 plus 6 times 4 plus 0 times 0. So this will be 30. So this will now be the product of A and B. So this will now be the answer. So now for letter B, this is B times A. So we just interchange the position of B and A, right? So this is matrix B and this is matrix A. So again, before we multiply this, we first have to check, okay, if it complies to the requirement, okay, for this matrices to be multiplied. Okay, so again, the size of our first matrix here will be 3 by 4. And the size of our second matrix here will be 2 by 3. So again, our rule here, the size of the column of the first matrix, it should be equal to the size of the row of the second matrix. But since this is not equal, okay, so we cannot actually multiply these two matrices. Okay, so again, these matrices cannot be multiplied. So that will be the answer for this problem. So let's proceed now to equality of matrices. Two matrices A and B are equal if and only if their corresponding elements are equal and if they have the same size. Okay, so we can only apply the equality of matrices, okay, if the matrices have the same size. Okay, let's say we have here matrix A and matrix B. So applying equality of matrices, okay, the elements from matrix A, okay, will just be equal to the corresponding elements of matrix B. So meaning to say, okay, your element A will just be equal to element E, your element B will just be equal to element F, your element C will just be equal to element G, and your element D will just be equal to element H. So that's how equality of matrices works. So let's solve this problem. Find the value of x and y if this matrix, okay, is equal to this matrix. So since these two matrices have the same size, so we can apply the concept, okay, of equality on matrices, no? So for our solution, no, so your x here, your unknown x here, it will just be equal to its corresponding element here, which is 0. No? So x it will be equal to 0. And for your y, it will just be equal to its corresponding element here, which is negative 1. So your y will be negative 1. Again, your x is equal to 0 and your y is equal to negative 1. So that's just how simple it is. No? Yan. These are the answers already. Now, let's proceed to transpose of a matrix. So, the transpose of a matrix is represented by A raised to T. Okay, so it is formed by interchanging the rows and columns of matrix A or vice versa. No, so let's say we have here matrix A. So these are the elements of matrix A, elements A, B, C, and D. So to solve for the transpose of matrix A, okay, we just need, okay, to interchange the rows and columns. Okay, so let's say we are just going to make your row here column, okay, in the transpose, okay, in the transpose matrix. So let's say this row, okay, AB, it will be column here in our transpose. Okay, and this row CD, it will be column here in our transpose. So this will be the transpose of matrix A. So again, we just interchange the rows and columns. Okay, so the rows here in matrix A will be the column here, okay, in the transpose. No? So that's how you get the transpose of a matrix. Now let's solve these problems. No, so we have to find the transpose of the following matrices. So these are matrix A, B, and C. So let's try to solve this. So for number 1, okay, so for the transpose of matrix A, so we just have to make your rows here, okay, column. Okay, so for your transpose, okay, for the transpose of A, again, it is A raised to T, okay, is equal to, so we just make this row column here, and we just make this row column here. So this will now be the transpose of A. Okay, now for the transpose of B, so again, we just interchange rows and columns here. Okay, so we just make the rows here, column here. Okay, so this row will be column here. This will be 1, 2, 3. And then this row 4, 5, 6, it will be column here, 4, 5, 6. And this row here, it will be column here. So this will now be the transpose of B. Now for the transpose of C, okay, so again, we are just going to interchange rows and columns. So we are just going to make the row here, column here. Okay, so this row 1, 2, 3, it will be column 1, 2, 3 here. Okay, and your row 4, 5, 6, it will be column 4, 5, 6 here. So this will now be the transpose of matrix C. Okay, so let's proceed now to properties of transpose of a matrix. So for all matrices A, B, and any scalar C, the following four transpose properties hold. Okay, so the first one, okay, if you have here A transpose and you try to transpose that, so it will just go back to matrix A. Okay, so this will be the first property. Now for the second property, let's say you have here a scalar quantity C and matrix A, and you transpose them. Okay, so you can factor out scalar quantity C, okay, and get the transpose of matrix A, okay? So for the third property, if A plus B is defined, so A plus B quantity transpose equal to A transpose plus B transpose. So meaning to say, if your A plus B is defined, meaning to say they can be added, no? So if they can be added, if you add them first, okay, and get their transpose, it will also be equal if you get their transpose first, okay, and then add them. Okay, so it will just be the same, no? So this is the third property. Now, for the fourth property, if AB is defined or product AB, okay, meaning to say your matrix A and B can be multiplied. Okay, so therefore your A B transpose is also equal to B transpose times A transpose. Okay, but this is not equal to A transpose, okay, times B transpose. Okay, so again, your if you have a product AB and get its transpose, it will be equal if you get the transpose of B and transpose of A and multiply them. Okay, but this will not be equal if you get the transpose of A and transpose of B and then you multiply them. So the position of B and A here will be crucial, no, because yun nga, it will not be the same here, ano, it will not be the same answer for this, no. So this will be the fourth property. So let's solve this problem. Let S1, S2, and S3 be the submatrices of this matrix A. So submatrices are smaller matrices, okay, that can be taken, okay, from your given matrix. No? So whose respective arrays or arrangement are the elements common to the following row and columns of A. So these are the given for the submatrices S1, S2, and S3. For your S1, it is row 2 and 3, and then column 3 and 4. So this will be the row and column of this submatrix 1. No? So rows 2 and 3. So these are rows 2 and 3, and then column 3 and 4. So your column 3 and 4 will be this. So meaning to say this is the submatrix that we are looking for. Okay, so these are the submatrices that are in row 2 and 3 and column 3 and 4. Okay, so this will be the S1. No? Now for S2, okay, so again, the given here is row 1 and 4, and then columns 3, 4, and 5. Now for S3, it is rows 1, 2, and 4, and columns 1 and 2. Okay, so after solving for these submatrices, we have to, that's the first question actually, no? You have to write submatrices S1, S2, and S3. Then we have to find the product of S1, S2, S3, and show that S1, S2, S3 transpose is equal to S3 transpose times S2 transpose times S1 transpose. So this is actually the fourth property in the transpose of matrices, right? So we will prove this fourth property, no? And for letter C, the question is, are any of the matrices S1 plus S2 transpose, S1 plus S3 transpose, and S2 plus S3 transpose defined? No, so we will start solving this. Okay, so this is matrix A. No, so for letter A, again, we are asked here to give or write the submatrices S1, S2, and S3. So for S1, this is rows 2 and 3 and columns 3 and 4. So this is row 2 and this is column 3 and 4. So this again, this is the matrix, submatrix that we are looking for. So we write it here. So this is 2, 8, negative 5, and 6. Now for second submatrix, that is rows 1 and 4. So this is row 1 and this is row 4. And then columns 3. Okay, columns 3. This is column 3. And then column 4 and then column 5. So we will write the corresponding elements again from row 1. Okay, and row 4 and then column 3. That will be negative 3 and 1. And then column 4, 7, negative 9. And then column 5, 0 and 5. So this will be the submatrix 2. Now for submatrix 3, this is rows 1, 2, and 4 and columns 1 and 2. So rows 1, 2, and 4. Okay, and then column 1. So that will be 10. Okay, that will be 10, 0, and negative 1. And then column 2, 0, 1, and negative 2. So this will be the submatrix 3, no? Now, for letter B, we have to find the product of S1, S2, and S3. Okay, so, and show that S1, S2, S3 transpose equal to S3 transpose times S2 transpose times S1 transpose. So, let's first solve for the product of S1, S2, and S3. So, this is your S1, no? So, this is your S1, this is your S2, and this is your S3. Okay, so we can solve for its product by multiplying first the first two matrices. Okay, so we can first solve for their product, and after that, the product will be multiplied by this. Okay, by the third submatrix, no? But also, you can also multiply the second submatrix to the third submatrix. So you can multiply them first, no, before, and after that, if you get its product, you multiply it here, no? But you cannot multiply this first matrix here or submatrix here, and then you multiply it in the third submatrix. You cannot do that, no? So you can only multiply matrices that are placed side by side, no? Okay, so you can multiply this first or this first. No, so in this case, we are going to multiply first the first and second submatrix or submatrices. Okay, so we multiply it. So our rule here for multiplication, okay, the number of a column, okay, of your first matrix should be equal to the number of row of your second matrix. So this satisfies the that condition. Therefore, we can multiply these two matrices, no? So this will just be 2 times negative 3, okay, plus 8 times 1. Okay, so that's our rule again, no? So you just have to multiply the first row here from your first matrix and the first column of your second matrix. So that will be 2 times negative 3, okay, plus 8 times 1. So that will be the element, okay, in the first row and first column since we multiplied first row and first column. Okay, now for this element, so you just have to multiply first row here to the second column. Okay, so that will just be 2 times 7 plus 8 times negative 9. Okay, now for this element, this is just the product of your first row and third column. So this will be 2 times 0 plus 8 times 5. Okay, now proceeding to this element, so this will be the product of your second row and first column since it is located in first row, second row rather, second row and first column. So this will be negative 5 times negative 3 plus 6 times 1. Okay, now for this element, so this will just be negative 5 times 7 plus 6 times negative 9. Now for the last element here, this will just be negative 5 times 0 plus 6 times 5. Okay, so simplifying this, okay, so we will multiply this also to the third submatrix, no, but we have to simplify this first. So simplifying this, this will just be 2 times negative 3 plus 8. That will be 2. And then we have here 2 times 7 plus 8 times negative 9. That will be negative 58. And then we have here 2 times 0 plus 8 times 5. That will just be 40. And then we have here negative 5 times negative 3 plus 6 times 1. That will be 21. And we have here negative 5 times 7 plus 6 times negative 9. That will be negative 89. And we have here negative 5 times 0 plus 6 times 5. This will be 30. Now, this will be the product and we have to multiply this further to the third submatrix. Okay, so again, we have to check if they can be multiplied. No, so the number of column, okay, of your first matrix, it should be equal to the number of rows, okay, of your second matrix. So in this case, it satisfied that condition. No, so we can multiply this. So let's start multiplying this. So we just multiply the first row to the first column. So that will be 2 times 10 plus negative 58 times 0 plus 40 times negative 1. So that will be the element in the first row and first column. Now for this element, it will just be 2 times 0 plus negative 58 times 1 plus 40 times negative 2. Now for this element, so we just multiply the second row and first column. Okay, this will be 21 times 10 plus negative 89 times 0 plus 30 times negative 1. Okay, lastly, for this element, this will just be 21 times 0 plus negative 89 times 1 plus 30 times negative 2. Okay, so simplifying this, this will be 2 times 10 plus negative 58 times 0 plus 40 times negative 1. That will be negative 20. And then we have here 2 times 0 plus negative 58 times 1 plus 40 times negative 2. So this will be negative 138. And then we have here 21 times 10 plus negative 89 times 0 plus 30 times negative 1. That will be 180. And we have here 21 times 0 plus negative 89 times 1 plus 30 times negative 2. That will be negative 149. So this will be the product of S1, S2, and S3. Now we are also asked here to show that S1, S2, S3 transpose is equal to S3 transpose times S2 transpose times S1 transpose. So let's first solve for the S1, S2, S3 transpose, no? So let's just take the transpose of this S1 product S1, S2, S3. So as getting its transpose, we just interchange the rows and columns. So this row negative 20, negative 138, we just make it the first column here, and then this second row 180 negative 149, we just make it the second column here 180 negative 149. So this will be the transpose of product S1, S2, S3, no? Now let's proceed to the next one. We have to solve for this. So now we will solve the product of S3 transpose, S2 transpose, and S1 transpose. So this will be your S3. So we are going to solve for its transpose. This is S2. We are going to get its transpose. And this is S1. We are going to get its transpose. Okay, so solving first for their transpose. Okay, so interchanging rows and columns. Okay, so this row will be column here. This row will be column here. This row will be column here. So this will be the transpose of S3. Now for S2, so this row will be column here. This row will become column here. So this will be the transpose of S2. And this S1 naman, no, for its transpose, this row will just be column here. This row will be column here. So this will be the transpose of submatrix 1. Now we are going to solve for its product. So again, you can solve for the product first of S3 transpose and S2 transpose, and then after solving for the product, we multiply it to the third submatrix, and we can also solve for the product first of this second submatrix and first submatrix. No, so we can solve for its product and multiply it to this submatrix 3, no? So but here, no, we are going to multiply first this submatrix 3 transpose and submatrix 2 transpose. No, so multiplying them. So again, we can check if they can be multiplied if the column of this first row or first matrix is equal to the row, okay, of the second matrix. So they are equal. So therefore, we can multiply them. So this will just be row times the first row times the first column. That will be 10 times negative 3 plus 0 times 7 plus negative 1 times 0. Now for the second element, that will just be first row times second column here. So that will just be 10 times 1 plus 0 times negative 9 plus negative 1 times 5. Now for this element, so this will just be the product of the second row and the first column. That will just be 0 times negative 3 plus 1 times 7 plus negative 2 times 0. Now for this last element, so this will just be the product of second row and second column. So that will be 0 times 1 plus 1 times negative 9 plus negative 2 times 5. So we have to simplify this before multiplying this to the submatrix 1 transpose. No, so let's simplify this further. So this will be 10 times negative 3 plus 0 times 7 plus negative 1 times 0. That will be negative 30. For 10 times 1 plus 0 times negative 9 plus negative 1 times 5, that will be positive 5. Now for 0 times negative 3 plus 1 times 7 plus negative 2 times 0, that will just be 7. Now for 0 times 1 plus 1 times negative 9 plus negative 2 times 5, that will just be negative 19. So this will be the product of S3 transpose and S2 transpose. We can now multiply this to the S1 transpose. So multiplying this, again, our rule, the number of column of your first matrix should be equal to the number of rows of your second matrix. So since they are equal, okay, we can solve them. Okay, we can multiply these two matrices. So this will just be row times column. So the first row times the first column, that will be negative 30 times 2 plus 5 times 8. Now for the second or for the first row, second column, this will just be negative 30 times negative 5 plus 5 times 6. No? Now for this element, this is in second row and first column. So you multiply second row and first column, that will be 7 times 2 plus negative 19 times 8. Okay, now for the last element, that will just be 7 times negative 5 plus negative 19 times 6. So simplifying this will be negative 30 times 2 plus 5 times 8, that will be negative 20. And we have here negative 30 times negative 5 plus 5 times 6, that will be 180. And then 7 times 2 plus negative 19 times 8, that will be negative 138. And then we have here 7 times negative 5 plus negative 19 times 6, that will be negative 149. Okay, so from here, this will be the S3 transpose times S2 transpose plus times S1 transpose. So this is actually equal, okay, or the same to the S1, S2, S3 transpose that we have solved from the previous slide. No, so therefore, S1 times S2 times S3 quantity transpose is equal to S3 transpose times S2 transpose times S1 transpose. So we have proved that property here in this problem. So for letter C, this is the question for letter C. Are any of the matrices S1 plus S2 transpose, and then S1 plus S3 quantity transpose, and S2 plus S3 quantity transpose defined? So defined meaning they can be the operation can be done, no? So for S1 plus S2, our S1 is actually this, right? So this is 2 by 2, and your S2 is this. So this is 2 by 3. So they cannot be actually added since they have they don't have the same size, right? So your S1 plus S2 transpose is not defined. No, now for S1 plus S3, so again, your S1 is 2 by 2 and your S3 is 3 by 2. So again, they cannot be added, so it is not defined. Now for S2 and S3, so also your S2 is uh, 2 by 3 and your S3 is 3 by 2, so therefore they cannot be added. So therefore S2 plus S3 transpose is also not defined. So there's no given here in letter C that is defined. So that will be the answer for this. None. So now let's talk about the symmetry of matrices. A square matrix is said to be symmetric if it is equal to its transpose. Okay, so symmetry on matrices can only be applied on square matrix, no, on square matrices. So if the matrix is not a square, no, so it cannot be symmetric. Oh, so again, it can only be applied to square matrices. No, so it is said here that a square matrix is symmetric if it is equal to its transpose. So let's say we have your matrix A, and this is a square matrix. And if we solve for its transpose, okay, as we know, its transpose will be this row will just be this column, this row will just be this column, this row will just become this column. Okay, so checking this transpose to this square matrix, so as you can notice, they are actually the same, right? So 253, 253, 517, 517, 374, 374. So they are the same. So meaning to say, okay, this matrix, okay, this matrix A is actually symmetric. Okay, so this is a symmetric matrix, no? Since the this matrix is equal to its or the same to its transpose. Therefore, it is symmetric. So that concludes our discussion about this topic. I hope you learn and attain the intended learning outcomes for this topic. And reminder that you have CM assessment tasks that you have to answer and submit. Okay, so study well. Bye-bye, class. Keep safe and God bless. Bye-bye.